Hi, y'all. Today I'm going to be talking about two different skills. We're going to be talking about solving systems with our calculator, which we've already done a little bit, but a little bit more specific today. And then the second one is going to be being able to write systems of equations from a word problem and then being able to solve them. So far, all of our systems, we have given you the equations, but sometimes on your test or in the EOC, you're going to have to write a system of equations to represent a real world problem, which this is really, it's the application. It's here's this problem you have in the world. So write yourself a set of equations. So first we're going to start with those calculator questions. So we're going to look at number one. We have y is equal to 1/2 x plus 3 and 3x plus y is equal to negative 15. Okay, if I want to be able to solve an equation with a calculator, both of my two equations need to be y equals. So I already have my first one as y is equal to 1/2 x plus 3. My second equation, though, 3x plus y equals negative 15, is not in y equals. So I need to move that 3x over first, which gives me y is equal to negative 3x minus 15. So now I have two equations that are both in y equals. So once I have two equations that's both in y equals, I can go to my Desmos calculator. And I can graph both of these equations in our Desmos calculator. So my first equation is y is equal to 1/2 x plus 3. So y is equal to 1 divided by 2, x plus 3. And then my second equation is y is equal to negative 3x minus 15. So y is equal to negative 3x plus 15 minus 15. Okay, so hopefully it's an easier situation. You can see right off the bat where they cross. If you can't find where they cross, you can always zoom in or zoom out. So just make it a little easier. I can come over here and zoom in. And then to find your answer, you just want to click right there where the two graphs cross, which is negative 5.143 and 0.429. So this is a question where realistically, if I try to solve this without a calculator, I would get nowhere near those two answers because they would be really, really hard. I wouldn't get numbers to cancel out. It would be big old gross fractions. So sometimes you actually have to solve a system of equations using a calculator. And we're always going to solve those systems of equations using a calculator with our graphing method. So let's go ahead and add these over to our notes. So negative 5.143 comma 0.429. And just like our Desmos calculator does, y'all, we want to round to the third decimal place. Okay, let's look at another example for calculator. So y is equal to negative 1/2 x minus 1, and y is equal to 1/4 x minus 4. So both of these are y equals, so I can go ahead and go straight here. And I can update, so negative 1/2 x plus 1, I believe. Nope, minus 1. So I'll fix that. And then 1/4 x minus 4. Okay, so because I zoomed in last time, my two graphs aren't quite going to be nice. So over here I can see, and these actually do cross, it looks like, at a nice pretty point, and they do. 4 comma negative 3. So 4 comma negative 3 is my answer. So sometimes with calculators, you're going to get nice pretty answers, and sometimes you're going to get gross answers like we did on number 1. Okay, so now that we've done our calculator question, let's look at our word problem questions. And with word problems, remember there's two different equations we can use. There's our standard, which is ax plus by equals c, with A and B being some number multiplying by my X variable or my Y variable, and C being some total. And then we have our slope-intercept, which is our y equals mx plus b, with m being slope, our rate of change, and b being our y-intercept, some initial charge or some starting amount. So with our systems of equations, you're going to have situations where you write the equation in standard form, and you're going to have situations where you write the equation in slope-intercept form. The best way to tell the difference is standard form is usually going to be talking about two different variables or two different things that are changing that add up to some total amount. While with slope-intercept form, you're going to be dealing with rates and an initial amount. So that's how you can kind of determine between the two. So let's look at number 3. So Brian and Ryan are racing to see who can get their community service hours for scouting completed first. Brian, who already completed 50 hours, plans to volunteer for 2 hours per week going forward. Write an equation for Brian's plan for community service hours. So remember we talked about in word problems, if we're dealing with linear, our giveaway word for slope is like per or each or every. So 2 hours per week. So that is right off the bat, I can see that as a slope. So I know I'm going to be writing this equation in slope-intercept. Okay, so let's determine our variables. So x is usually our independent variable, which is typically time. And we can see in this question, we're talking about hours. So x would be our hours. Y being our dependent variable, it's whatever in the problem is dependent upon x. So what is dependent upon x? Scratch what I said about hours. So this question is actually a little confusing because the hours is the amount and the week is the time, because he's doing hours per week. So think of hours as like an amount. Like you have to get so many hours of community service. So weeks is actually his independent, and hours is dependent, because the amount of hours he would have completed is dependent upon how many weeks have gone by. Okay, so now there's two pieces of information I'm looking for if I'm writing this in slope-intercept. So slope-intercept, I need my m and I need my b. M is your slope. So we already said per is our slope word. So 2 hours per week means we have a slope of 2. Then b is our y-intercept. So our y-intercept is some initial amount. And Brian, who already completed 50 hours, so his b would be 50. And then we can write our equation as y is equal to, not 50, 2 x plus 50. Okay, so he has that slope of 2, and then he has that y-intercept of 50. So let's look at our second equation. So we talked about Brian, now let's talk about Ryan. Ryan hasn't started yet, but plans to dedicate 4 hours per week to his volunteer project from now on. Okay, so we still see that per, so Ryan's equation is still going to be in slope-intercept form. And Ryan hasn't started yet, so if he hasn't started, that means he doesn't have an initial. So his y-intercept really is just, it's 0. So we want to have the exact same x and y, because when we solve for our answer, we want to solve for x's and y's as if they're the same variable. So x is still weeks, and y is still hours. M in this case, though, he's dedicating 4 hours per week, so 4. And then he has not started yet, so his initial amount is just 0. So our equation 2 is y is equal to 4x. And then you can write the plus 0, or you can just not write anything at all, because not writing anything is the same as adding by 0. Okay? So then let's actually solve this question. So before too long, the boys will be tied with the same number of volunteer hours. How many hours will each boy have volunteered by then? So let's graph both of these, which I'm going to show you how to do this by hand, and I'm going to show you how to do this in your calculator. So y equals 2x plus 50. I'm going to graph in green. So we'll start here at 50. And then after 5 weeks, because this goes by 10, so after 5 weeks, he's doing 2 hours each week. So we go up by 10, and then up by 10, and then up by 10, because every week I'm increasing by 2. So that gives me my line there. And then for my second equation, for Ryan, we'll do him in blue. He is starting at 0, but he's going by 4 each week. So starting at 0, but after 5, he's going to be at 20. And after 10, so another 5 weeks, he's going to be at 40, and then 60, and then 80, and then 100. We can just add our arrows on because they will keep volunteering after their 25 or so weeks. So we can see pretty clearly, y'all. Right here on our graph is our point of intersection. Okay? And our point for that is actually, if we can read our graph correctly, it looks like 25 weeks. And it's at y equals 100, so 100 hours. So to answer our question, how many hours will each boy have volunteered by the time they will be tied? They will both have volunteered 25 hours. So with word problems, sometimes you don't need to necessarily find the full point of intersection. You only have to give me one of the variables. So in this case, we solved for the y variable, the amount of hours they would have when they are both tied. So the amount of hours they would have at that point of intersection. So something to kind of keep in mind with word problems is your answer isn't necessarily always that point of intersection. Sometimes you just use the point of intersection and then it's just going to ask for either the x value of the point of intersection or the y value. Okay, so that was a word problem where both of the equations were slope-intercept. Now let's look at another word problem with systems, but this time we're going to use standard form instead. So Kim's school is selling tickets for a fall concert. On the first day of ticket sales, the school sold 3 adult tickets and 9 child tickets for a total of $45. Write an equation for the first day of ticket sales. So what you should see is that we have 2 different things that are changing. We have the number of adult tickets and we have the number of child tickets. So we have 2 things we don't know, which is the number of, or the cost of the tickets. Okay, so because we have 2 unknowns, we'll give one to x and one to y. It doesn't matter which one you pick. I usually just go with the way it goes in the problem. So adults comes first. So we can say x is adults. And then y is child. And then $45 is our total. So it's going to be what our equation is equal to. So we're going to do 3 times x because 3 adult tickets. So 3 times x plus 9 times y because 9 child tickets equals $45. So how this equation reads is that if I were to buy 3 adult tickets and 9 child tickets and add that total amount of money together, it should equal $45. Okay. Second piece, the school took in $50 on the second day by selling 10 adult tickets and 5 child tickets. So for your second equation, just like last time, we want to make sure our variables are still the same. So x is still adults and y is still children. This time though, 10 adults and 5 children. So 10x plus 5y is equal to 50. Okay, and then once again, we want to graph the 2 equations and find the solution. But because we had to do the 2 equations in standard form instead of in slope-intercept, we don't have our 2 equations being solved for y yet. So we have to first solve those 2 equations for y. So it doesn't matter which one we want to start with. Let's start with just equation 1. So 3x plus 9y is equal to 45. So I can minus 3x, which gives me 9y equals negative 3x plus 45. Divide by 9, divide by 9, divide by 9. And we get y is equal to negative 1/3 plus 1/3 x plus 5 for our first equation. Our second equation, we have (10x plus 5y equals 50). So once again, minus 10x, minus 10x. So we get 5y equals negative 10x plus 50. Divide by 5, divide by 5, divide by 5. And we get y is equal to negative 2x plus 10. And once again, we're going to graph both of these on the same graph, and then I'll show you how to do them in the calculator as well. So y equals negative 1/3 x plus 5. So start here at plus 5. And then we are rising by 1, running by 3, but going down. So down 1 to the right by 3, down 1 to the right by 3, down 1 to the right by 3. And same thing in the other direction. And then I can go ahead and add in my line. And then here for my other one, starting up at positive 10, but going down by 2 each time. So down 2 to the right by 1, down 2 to the right by 1, down 2 to the right by 1, and so on. And then, of course, I can add in my line. It's not a very straight line, but so then from here, we can see by zooming in that our intersection point is here at 3, 4. So what does that mean? So 3, 4 is our point. X was adults. Y was children. So that means adults are $3 and children is $4. Okay, weird. Usually children are cheaper, but that's just how this problem worked out. Okay, now I will show you, because you're probably like at the end, Mr. Arbone, I don't know if I'm really confident in that point. It looks like it's a little off from 3, 4. Well, you can always use your calculator. So we can go to our calculator and type in the same y equals. So y equals negative 1/3 x plus 5. And y equals negative 2x plus 10. And once again, we can go and find that point. And we should get the same point, 3, 4. Okay, so you can always go and check these in your calculator. Let's do the other one, number 3, just to be positive. So y equals 2x plus 50 and y equals 4x. So y equals 2x plus 50 and y equals 4x. This one's a lot bigger, so we're going to have to zoom out a bit, but we can eventually find our point of intersection. Once again, click right there, 25, 100. So you can always, as long as you get these into y equals, you can graph these in Desmos, and then you can find that point. So graphing, obviously, it's good to know how to graph by hand, but you can always use your Desmos calculator to check your work, and that's going to be really important with these word problems. So with these word problems, always, always, always set them up correctly, and then if you can solve both equations for y, you can use your Desmos calculator to get your answer. You don't have to do all the work by hand. So it's kind of a nice little extra advantage you'll have. So y'all, that is solving systems by calculator and writing systems and solving systems from word problems. And that is it. Thank you.